Vision is how we teach machines to see, from raw pixels through convolutions, all the way up to promptable foundation models. A vision model answers one of four questions: what is it? Classification, where is it? Detection, like YOLO, which exact pixel? Segmentation, like UNet and SAM, or make new images generation. It starts with the image itself. To a computer, an image is a three-dimensional tensor, height by width by channels. A color image has three channels: red, green, blue. A 1024 by 768 image is shaped 3 by 768 by 1024. And here's the key idea. After the first convolution, the channels stop meaning colors and start meaning learned features. Before any of that, we normalize, divide by 255, then subtract the mean and divide by the standard deviation. And you do it the exact same way at training and at inference. Zero-centered inputs give a far better behaved loss surface. Why not just flatten the image into a plain neural net? Two reasons. First, parameters explode. Flatten a 224 by 224 image and connect it to 1000 units, and the first layer alone needs 150 million parameters. The budget is gone before it learns anything. And second, there's no translation invariance. A dog in the corner activates completely different neurons than a dog in the center, so the network would have to relearn dog for every position. The fix is the convolution. Slide a small filter across the image, and at every position, compute a dot product. Multiply the filter against the patch, sum it up, add a bias. A horizontal edge filter, for instance, fires wherever the bottom of a patch is brighter than the top. The output is a feature map, a grid showing where that pattern was found. In symbols, output ij equals the sum over the patch of the input times the kernel plus b. Use many filters and you get many feature maps. 64 filters of 3x3 turn a 3-channel image into 64 channels. And here's the magic. A 3x3 filter over 3 channels is just 28 parameters, so a 64 filter layer is under 2000 versus 150 million for the fully connected version. About 84,000 times fewer, because the same filter is reused at every position. Stack these and the features build up on their own. Edges, then textures, then eyes and wheels and faces. Nobody assigns those meanings, they emerge. A few mechanics. The output size is the floor of input plus 2p minus k over stride plus 1. Padding keeps the size, stride 2 halves height. Between convolutions we apply ReLU, the max of 0 and x. Without a nonlinearity, stacked layers collapse into one. The standard block is conv, BatchNorm, ReLU, and pooling shrinks the map by keeping the strongest response in each window, adding a little translation invariance along the way. Two ideas explain why depth matters. The feature hierarchy. Early layers see edges and colors, middle layers corners and shapes, deep layers whole objects, and the receptive field, the patch of input a neuron can see, grows with depth. End stacked 3x3 layers give a receptive field of 2n plus 1, and striding doubles it. That's why the high-level concepts live deep. By then, one neuron can see the entire object. Put it together into a full CNN, and a clear pattern appears. The spatial size shrinks, 2024 down to 7, while the channels grow, 3 up to 512, trading resolution for meaning. Then a global average pool and a final layer give class probabilities. Three ideas hold modern CNNs together: ReLU from ResNet, so gradients flow; batch normalization, which stabilizes and lets you go deeper; and residual connections from ResNet, output equals x plus block of x. The single most important idea since convolution, and the very same skip path used in transformers today. Now detection. Where are the objects? The old way proposed regions and classified each one, sliding windows with handcrafted features, or R-CNN running a CNN on 2000 proposals, 40 seconds an image. YOLO reframed it entirely, detection as one regression problem, resize, run a single CNN threshold and cleanup, one image in, all the boxes out, you only look once. YOLO splits the image into a 7x7 grid, and each cell predicts a couple of boxes plus class probabilities. The rule, whichever cell contains the object center, is responsible for it. One object, one cell. The whole thing is a single output tensor, 7x7x30, two boxes of 5 coordinates, plus 20 class scores, produced by 24 convolutional layers in one pass. Each box is 5 numbers, a center relative to its cell, a width and height relative to the image, and a confidence, the probability an object is there, times the IOU. One number for both is something here, and how good is the box? IOU itself is the intersection over the union of two boxes, the universal quality metric. YOLO produces 98 raw boxes, and non-max suppression trims them to a handful. Sort by confidence, keep the best, drop anything overlapping it too much, and repeat. Segmentation labels every pixel. Semantic segmentation gives each pixel a class. Instance adds which object it belongs to. Panoptic does both. But there's a core tension. You need deep semantics to know what something is, and full resolution to know exactly where. The first attempt, the FCN just dropped the dense layers and upsampled the tiny 7x7 map backup. But you can recover resolution, not detail you threw away, so the masks come out blurry. UNet solves it with its signature shape. An encoder goes down to deep compressed meaning, then a decoder mirrors it back up to full resolution. The secret is the skip connections. At every scale, sharp features from the encoder are carried straight across to the decoder, so deep semantics meet crisp edges. It trains on as few as 30 images, gives razor-sharp masks, and the very same UNet runs inside Stable Diffusion. For instance segmentation, Mask R-CNN treats the problem as detect plus segment. For each detected box, a small network draws a binary mask. Its key trick is RoIAlign. Instead of rounding coordinates, it uses bilinear interpolation for sub-pixel accurate sharp masks. And then came segment anything, SAM. One promptable model, click a point or draw a box, and it segments whatever you indicate, zero shot, on objects it has never seen. Trained on 11 million images and over a billion masks, it's segmentation's foundation model, the same move GPT made for language. Finally, transformers came for vision too. The vision transformer cuts an image into patches, treats each patch as a token, adds positions, and runs a standard transformer. Attention in place of convolution. And clip trains an image encoder and a text encoder into one shared space, so a picture and its caption land close together, powering zero-shot classification, image search, and every text-to-image generator. From pixels to features to objects to meaning, that is vision.